Hi everyone, and welcome to Lecture 2. In this lecture, we're going to discuss Chapter 1 of your textbook, From the Big Bang to the Blue Marble, with the blue marble being Earth. And so in your title slide, I've got a picture of a rather zoomed out view of a portion of the universe. This is called the Pillars of Creation area in the Eagle Nebula, and this was a photo taken from the NASA Hubble Space Telescope in the 2010s. And on the right we have a picture of Earth from space, also from NASA at the International Space Station. So in Lecture 2A, we're going to discuss the formation of the universe and the Earth, and afterwards we're going to discuss in a little more detail Earth's spheres and Earth science criteria. So, without further ado, let's get started. I want you to get started by reading this quote from your textbook. Prior to the emergence of modern scientific thinking in the 16th century, people in Western cultures assumed that the stars were anchored to the surface of a distant sphere surrounding the Earth, and that the sphere, along with all other celestial objects, including the sun, circled the Earth. In other words, people favored a geocentric model in which the Earth lay at the center of the universe. So, I want you to imagine this distant sphere, then draw a picture of the geocentric model of the universe. And the drawing can include anything you want: humans, animals, a god, and include annotations and labels to explain it. This will be a part of your lecture activity. Feel free to pause the video and do this. As a reminder, I need you to require your online textbook as soon as possible to start completing your homework assignments. Thank you. So, let's talk about our basic image of the universe. The universe is made of galaxies, nebulae, stars, planets, and many other celestial objects. It's important to note that galaxies are much bigger than nebulae, contain nebulae, and nebulae contain stars, and solar systems contain planets, and in that order. Here is a picture on the left of the Milky Way galaxy as seen in the night sky of Washington in northwest United States. This picture shows the Milky Way, a portion of the Milky Way galaxy. It's important to note that we are also within the Milky Way galaxy, so we're looking at another piece of it from the inside. Modern cosmology is the study of the structure and evolution of the universe. So throughout human history, there have been many different types of cosmologies that have sought to understand and provide reasons and stories, which we consider now as myths and legends, of the origin of Earth and the origin of the universe. And in this class, we're going to study modern cosmology, meaning the scientifically based study of the structure and evolution of the universe. In order for us to do that, we need to first talk about measuring distances in space. And this was how the first astronomers started understanding how far celestial objects were from Earth and how far they were from each other and how much time it took for them to become at these great distances from one another. So first we'll mention the speed of light, which is 300,000 kilometers per second. If you wanted to try to put that in something that was more understandable, you may imagine multiplying 100 miles an hour in a car, for example, by 7 million times, and then you have the speed of light, more or less. 1 light year is the distance that light travels in a year, and that is 9.5 trillion kilometers. So with these large scales, it's often difficult to understand the size. That's why we make it easier. The Andromeda Galaxy is the nearest neighbor to the Milky Way galaxy, and for example, that is 2.5 light years away from us. So about 25 trillion kilometers away. The formation of the universe started with the Big Bang theory, and started with the Big Bang. And the Big Bang theory is that all matter and energy initially existed in an infinitesimally small point called a singularity. And that point began expanding outward about 13.8 billion years ago. The prefix, or the GA, stands for billion years ago. So on the left, you've got an image of the Big Bang, an artist's rendering of what the Big Bang would look like on its left side when it began, and then at present as objects are spreading out from one another. And a great way to think about this is the muffin bread analogy, or the raisin bread analogy. And that's a great way to think of the expanding universe. So Edwin Hubble discovered that most all galaxies were moving away from Earth and one another when the speed of light was determined back in the 1920s. And the raisin bread analogy for the expanding universe shows us that as the dough expands, if you were to cook a piece of bread or chocolate cookie, for example, each raisin moves further away from one another as the cooking process takes place or as time passes by. So this is an easy analogy for us to think of in the expanding universe. This next slide is a video clip of the different sizes of celestial objects, starting with planets, going up into suns, nebulae, galaxies, and the known universe. I will encourage you to watch it in the discussion posts or for the lecture activity, but for now we will skip it. Once you've watched the video, and listened to this portion of the lecture, I'd like to present to you a question. I'd like you to look at the images of the 4 galaxies on the left, A, B, C, and D, which are all approximately the same size. And based on the raisin bread analogy of the universe and our perspective of viewing these galaxies from a fixed point on Earth, which galaxy do you think is the closest to us, and which is the farthest, and why? So in order for you to answer this question, you need not only the raisin bread analogy, but I also can provide you with this image on the bottom right, which is an image of railroad tracks. Now I want you to think about perspective in this image, and I want you to ask yourself, is the track closest to my viewpoint larger, smaller, or the same size as the track that is furthest away? And the answer that you should get for yourself is that these tracks are all the same size, but it's just our perspective is showing them look smaller as they are further out and further into the distance. And so I want you to use that idea along with the raisin bread analogy and your knowledge of the size of these galaxies to answer the question for your lecture activity. Thank you. In addition to learning about how the universe formed, we want to understand what formed when the universe formed. So here I've got a figure of the formation of the elements, including the periodic table. As an aside, you may find that actually you could learn pretty much all of physics and chemistry and natural science by looking at a few diagrams and understanding them in depth. The periodic table would be one of those diagrams. Another one of those diagrams that would help us understand the speed of light and distances between objects in space would be the electromagnetic spectrum. But anyway, back to the periodic table. So, during the Big Bang, nucleosynthesis, so this is when nuclei were formed, atomic nuclei, this produced only two elements, helium and hydrogen, the first two elements of 1 and 2 protons, respectively. Then, as stars began to form, we got stellar nucleosynthesis. So as the first stars in the universe formed, we continued to form heavier elements all the way up to the element iron at atomic number 26, also having 26 protons. Elements heavier than iron formed during supernova explosions, which is known as supernova nucleosynthesis. And over time, they've built up and been incorporated into other stars. And as they've exploded again and again and become more dispersed and segregated, they have become the building blocks of planets. So this kind of explains our idea of what we call nebular theory. So nebulae are these big cosmic groups of ice and dust and gas. Take note that ice and dust have important strict definitions in your textbook. And here's an example of the Orion Nebula, which is 24 light years across and has stars currently forming in it. But the first nebulae were formed about 200 million years after the Big Bang, and as they collapse, they form protostars and the first stars. So imagine these images were forming some of the first elements of the periodic table. Protostars can be explained through when the nebular cloud collapses, it starts to spin as a result of all of the material coming together and all of their gravities interacting with one another. And as that material gets smaller into a smaller space, it rotates faster and faster. And the analogy you can use for this is a figure skater pulling in their arms while they're spinning. As their mass becomes more centered, their velocity increases, so the spin becomes faster. Actually, this turns out to flatten the matter in the disk around the evolving protostar. And the protostars produce the first generation stars in the universe. Typically, the largest stars are the hottest and have the shortest lives and end in supernova explosions only within a few million years. So here's a picture of the Crab Nebula and a supernova around 1000 Common Era. The sun, our star, powers Earth systems and is the body around which all planets rotate or orbit. And our solar system is made up of those planets, which include the terrestrial planets, Mercury, Venus, Earth, and Mars. The giant planets, which are further from the sun, Jupiter, Saturn, Uranus, and Neptune. These are also known as the Jovian planets, and other material, which include moons, asteroids, dust, ice, and comets, which are spread across the solar system. Our solar system formed kind of similar as nebulas and stars. So we've got condensation theory, which talks about a rotating protoplanetary disk made of gas, ice, and dust. Excuse me. The sun formed, and then these planets were formed through condensation theory. So the solar system formed through this condensation theory. Dust and ice accumulated into planetesimals, and as a result of gravity, some of those planetesimals accumulated into larger protoplanets. So at point A here, you've got the disk forming and then the sun forming eventually in the planets. So Earth began as a large planetesimal or group of planetesimals around 400 to 800 kilometers in diameter. And gravity pulled all of this matter into a sphere when its mass was sufficient. Earth had an internal differentiation when it began. So all planetesimals, once they reach a certain size, have internal increases in temperature. So you've got that high pressure. Eventually that high pressure and temperature can melt the rock on the deepest parts of the inside. And that forms a metallic core and a rocky mantle. So all of the most dense elements like iron went straight to the core, and the lighter elements exist on the outside of Earth. If we want to think about Earth's interior in a detailed view, we can divide into the core, the mantle, and the crust, where the crust is the least dense, the core is the most dense, and the mantle is in the middle. Crust is the thinnest layer on Earth, and the mantle is the thickest. No, excuse me, the core is the thickest. Finally, we'll refine the view of the interior structure of the Earth, where we have the mantle divided into portions and the core divided into an outer and inner core. And the way that we know that there are these divisions are through seismic waves or earthquake waves, which are able to pass through some portions or some layers of this of Earth and not through others. And that ends lecture 2A.